All right, so we've dealt with acceleration based upon change in speed. Let's now deal with acceleration based upon change in direction. Because again, there's acceleration if there's a change in velocity. So acceleration, change in velocity over the change in time. So I have some object that's traveling in a circle at some constant speed. That's what this is supposed to indicate, that the initial speed and the final speed are just equal to what I'm going to call v. This angle right here is the same angle as that phi. And so if I want to be able to find the change in velocity, I need to be able to break this up into rectangular components to make life a little bit simpler. So this one, I got some horizontal and vertical bit there. All right. So my initial velocity is v cosine phi, let's establish I hat, j hat. I hat plus v sine phi j hat. So just broke it up into two components. The same thing over there. V final is v cosine phi I hat minus v sine phi j hat. The reason we're doing this is to find acceleration, I need to find the change in velocity.
What's the difference? What's the difference between phi and theta?
The phi looks like a null sign and theta looks like yin yang.
They mean the same thing.
Yeah, typically when dealing with rotation or angles, you typically use Greek letters. Phi and theta are the two most common. I think it's in one of the videos. Can't remember. You can use pretty much any Greek letter for angles, but please don't ever use pi as a symbol for a variable or an angle. It was a master of physics textbook. It took me about 30 minutes to figure out that pi was not the number pi, but a variable. All right. If ever I'm trying to find change, how do I find change?
Initial minus final.
Or,
Final minus subtract.
that's the one.
Minus and subtract.
Yeah, you're definitely going to subtract, but it's always final minus initial. So v final minus v initial. And I'm going to make delta t just time, however much time it took place. Well, I have Vf and Vi over there because I set up a nice symmetry for this to work. So I got V cosine phi I hat minus V sine phi j hat minus V cosine phi I hat plus V sine phi j hat. And the dots eventually showed up. Okay. Divided by time.
Why is it subtract and not addition? And why is you? Never mind. Wait. Okay. Yes, never mind. I figured it out.
Okay, all right. Maybe that will always work, I just stare. The realization will be there. So if we simplify this numerator, what goes away?
V cosine I hat.
Yeah, I got V cosine I hat minus V cosine I hat, those are gonna go away. I'm left with negative sine phi j hat minus V sine phi j hat. So what I'm left with is minus 2 V sine phi j hat divided by time. Not a particularly useful equation at the moment, but we're getting there. All right. if the amount of time it takes to get from here to here is t, and it's traveling at a constant speed, what is this distance? It's traveling at a constant speed for,
Speed over time.
say it again?
Speed over time.
Not for distance.
It's the arc length, which is, you're asking for the length of that?
I'm asking for the arc length
Um,
in terms of speed and time.
in terms of speed and time.
Speed times time?
Yes, speed times time. You're traveling 50 meters per second for 5 seconds, you're pretty good 250 meters. So it's just the speed times the time. So the arc length here is equal to VT. Now I think into what Coy was heading towards. What's the relationship between this angle, the arc length, and the radius of this curve?
Two pi times the radius times 2 phi equals the arc length.
I think it's a long way. So you said 2 pi times the radius
Times 2 pi over 360 or 2 pi.
times 2 pi over 360.
No, times 2 phi
2.
over 2 pi or 360, whichever one you want to do.
Oh, it's equal to the arc length.
Yes.
Yeah, that is true. That's in general. If I take the radius of any circle, I take that radius and I wrap it around the edge here, so that the arc length here is the same as whatever the radius of the circle is. This angle here that is subtended, that is what 1 radian is. That's by definition a radian. So the number of radians around a whole circle, well, how many radii can I wrap around it? Well, I can wrap around 2 pi radiuses, circumference of a circle, around the outside here. And so therefore, the angle here is 2 pi radians for an entire circle. So that's why 2 pi radians is equal to 360 degrees. We can generalize it a little bit more. Instead of looking at the entire circle, look at just part of the circle. And always think of standing room only. That the arc length is equal to the radius times the angle, if this angle is in radians. So getting to what Coy had said there, my arc length, VT, is equal to the radius times the angle, which is 2 phi, which is what you get right there. So we have a relationship here. I now know that time is equal to 2r phi divided by the speed. Just solve it for time. So I can make that substitution. So I got minus 2 v sine phi j hat divided by 2r phi divided by speed. Well, I'm dividing by a fraction, same as multiplied by the reciprocal. 2's cancel out, and so I end up with negative v squared sine phi j hat divided by r phi. Stay with us, Miranda.
What is that song that you keep saying? Five?
Phi.
And what is that equal?
It's the angle, I defined phi over here, that the angle between this position and that position, this thing that's traveling in a circle, is just 2 times phi.
Okay, because that's how I write my zeros, so it's like.
Yeah, with my phi's, I tried to draw the line more up and down and longer. With my zeros, when I cross my zeros, trying to do it at a jaunty tilt, not quite as long of a line.
My question.
Yes,
Where did Corey get that equation from, the two IR?
You just pulled that right out there.
You gave us, so if that's equal to S, is that the same equation as R25?
is this the same as that?
Yeah.
Yeah, it is, because if the 2 pi cancels out,
Oh, okay, so, I don't get the correlation between those, but what's the correlation between that, the red one, and the circle that you drew?
that it's proportion, since 2 pi r is the circumference, which would relate, so 2 pi arc length relates to 2 pi radians, and it's proportional, so whatever my arc length happens to be, it's gonna be proportional to the angle. So if my arc length is this long, well, if that's 1.5 radii, that's 1.5 radians. I feel like that, my answer was not satisfactory there. You wanna try it again?
Trying to figure out how to word my question. So you have the radius.
Yep.
And then that arc length you drew is just the same length as the radius.
Yeah, if I took a string here to get the radius, and then I took my string and I just started wrapping the string around the edge.
Okay, that's one radius, the angle of that is one radius.
Correct, by definition.
Okay, so,
Because the mathematicians are trying to come up with an angle measurement that was natural and not one that was man-made, 360.
so why is 2 pi radians 360?
Because if I take my radius, how many times can I wrap a radius around the edge of a circle? I can do it 2 pi times. So if I get 2 pi radii around the edge, that means I have 2 pi radians for the angle.
So that's about 6.3 times, right?
Yeah.
Okay. I don't even know what my question is anymore, I just don't,
In Blackboard, I think under chapter 1, there's some videos on some of this stuff. I don't know if it's gonna answer your question or not, but
unicircles.
there's one specifically on radians and the Babylonians that's mixed in with that. That's where the 360 comes from. And then I get into the unicircles on in a different video.
We're just gonna keep on pushing.
So, is there a question on the floor at the moment? All right, so let's finish this up. Now, what I've done here is, this is the formula for the average acceleration, but I want the instantaneous acceleration. I want the acceleration when it's, say, right here. In other words, as phi becomes smaller and smaller, what happens to that? And this gets into what's called the small angle approximation. You can try this on your calculator if you have it. You have to be in radians though. That if the angle is much less than 1, so if you got the 2 less than symbols, that means much less than, then phi is approximately equal to the sine of phi. You've had some calculus, you've had some calculus. Anyone else who's had calculus?
Who said?
You've had some, okay, so just go on.
Cooper has, but he's not.
Yeah. How far have you gotten?
Well, I took a calculus course last year at Parkland,
Okay.
and I'm taking it right now in this quarter.
Okay, got 1?
Yeah, I haven't heard of small angle approximation.
Something that you will eventually face, and this is just a 15-second aside. Sine of phi is equal to phi minus phi cubed over 3 factorial plus phi to the 5th over 5 factorial minus phi to the 7th over 7 factorial, etc. If phi is a small number, then that small number cubed to the 5th and to the 7th becomes so incredibly tiny we can ignore them, and it ultimately ends up with those. If phi is small enough that these are approximately equal. So later on when you see that, or if any of you see that, you can go, I've done that for years. So if the angle is small, since we're dealing with an instantaneous value, the phi and phi, those phi's are small, these cancel out. And what I'm left with is my acceleration is negative v squared over r. This j hat. Making it slightly more general. That negative j hat means it's pointing towards the center, because I'm looking at the top here. Matter of fact, it's always going to point towards the center no matter where I am. So generalizing that, my centripetal acceleration, because it's pointing towards the center, negative v squared over r hat. And r hat is just a unit vector that points away from the center. R hat, unit vector pointing away from center. And since AC points towards the center, that's why the minus sign's in front. Now, all that's well and good, but I'm sure the question that's popped up in most of your minds is, hey, that's great, but how does that really work in conjunction with the stuff that we just did with Newton's laws? And I'm glad you're thinking that. Questions before we actually do that? So let's set up a situation here where I have a table with a hole in the middle. So this is a sort of a side x-ray view. I've got a hole in the middle of the table. I've got a mass sitting right here, attached to a string. String comes down, it's attached to another mass. From an overhead view, what this would look like is you've got a table right here, you got a hole in the middle, got a mass here that's going to be basically going around in a circle, and a string that's attached to this hanging mass down here. And I'm going to cleverly call this mass 1 and mass 2. Questions about visually what's going on here? All right. Force diagram. I got the two masses that I care about. I got M1 and M2. Although not required for the force diagram, M1 is going to be traveling in a circle at a constant speed. And M2 is in static equilibrium. So mass 2 is just going to hang there.
Are we gonna find out how much box 1 has to be to spin in a circle and hold mass 2 up?
Yeah.
Okay.
Yeah. So let's go ahead and state that. This V1 such that I guess mass 2 is in static equilibrium. Not quite the same thing, but an approximation. Now, if I go too slowly, this should fall, as it's doing right now, and if I go too fast, it should go up. So there is a sweet spot, well, with friction, a sweet range, where this will travel in a circle, and this basically is as close to static equilibrium as I can muster. Now, it's not quite the same thing, because in that case right there, the string is horizontal, and in what I'm doing here with swinging this, it will sag some. All right, force diagram. What are the forces acting on what?
Like,
Gravity on both of the, or weight on both of the masses.
So W2, W1, okay?
Tension.
All right. Okay, tension acting this way, and tension acting this way.
The normal force,
On,
M1.
yeah, something's holding it up, so I got a normal force there. There's a normal force on the string too, but I really don't care about the string at the moment, from a physics point of view. All right, equations of motion. Or, strike that. Direction of acceleration. What is the direction of the acceleration of mass 2?
0, or,
Going with the spirit, yes, that it's an equilibrium acceleration 0. All right, mass 1, what is the direction of its acceleration?
Into a circle, so.
That's,
Not quite sure what direction you were pointed in at that moment.
Me neither.
he's talking about like in a circle, so it would go that way, and just going counterclockwise.
No, the acceleration would not be in that direction.